Look at this system of masses and springs. The movement may look periodic, but it most definitely is not. This system is known as a system of coupled oscillators, and it has very interesting properties. Analyzing it can teach us a lot about differential equations, periodic functions, and more. Those of you who have studied high school physics probably remember learning simple harmonic motion. This is any motion with a mass which has a restoring force that is proportional to the mass's displacement. In other words, the mass is pulled with more force as it moves away from the center. We can analyze this movement using Newton's second law. The force acting on the object can be expressed as F equals negative kx, and since F equals ma, I can rewrite this as ma equals negative kx. Now, I'm going to rewrite a as x double dot. This just means the second derivative of x, displacement, with respect to time, and so it's just another way to write acceleration. Now, I'm going to move everything to one side, and I have x double dot plus k over mx equals 0. This is known as a differential equation, because we're looking for a way to describe the displacement of a mass in harmonic motion by using its relationship to its derivative. The solution to this equation is x equals a cosine square root of k over mt plus phi, where a and phi are starting conditions of the system. Remember this solution, because it will be important later. We can confirm this solution by taking the second derivative of our solution and placing it in the original equation, like so. We can see that after substitution, the equation simplifies into a true statement, and therefore our solution is correct. Okay, so we've analyzed simple harmonic motion for one body, but what if we added a second? We now have two bodies and three springs. We can define a new axis for both bodies such that they're both at x equals 0 when they're at equilibrium, and their positions will be denoted with x1 and x2. We can analyze the net force acting on both bodies in a similar way as before, except we now have the middle spring. The extension of the side springs is just x1 and x2, as they are the displacements of the bodies from equilibrium. The extension of the middle spring is dependent not just on one body, but both. Specifically, its extension is x2 minus x1. We can assume that all springs have the same proportionality constant, k, and that both bodies have the same mass, m. We can find the net force acting on both springs and simplify it into this expression. We can then similarly replace F with mx double dot and obtain these two differential equations. These equations may be a bit more tricky to solve, but we can use a trick and both add them together and subtract them from each other. This leaves us with these two equations. We can now create two new variables, q1 and q2, which equal x1 plus x2 and x1 minus x2, respectively. This may seem strange, but watch what we can do now. We can easily substitute q1 into the added equation to obtain this. We can then do the same by substituting q2 in the subtracted equation. These equations are just our simple harmonic motion differential equation from the beginning, and we can solve them both in the same way. We can use the definitions of q1 and q2 to get x1 and x2 back, and we get these two equations for the position of the bodies as a function of time. Now we can get back to what I said at the start, that the movement is not periodic. The position function is the sum of two sine waves, which are both periodic, so you might think that the function itself is periodic, but we need to look at the periods of the sine waves. To find the period of the sum of two sine waves, we need to look at the periods of the individual sine waves. The period of the sum will be the lowest common multiple of the two periods. This makes intuitive sense, because both sine waves need to start a new period at the same point for their sum to also start a new period. For our uses, we can ignore a and phi from our position function, because they don't affect the period. The problem with our position function is that the ratio of the two periods of the sine waves is square root of 3, which is irrational. Therefore, there is no point at which both sine waves will finish their periods together, and so our position function is not periodic. So, while one mass moves in simple, periodic motion, we can introduce a lot of fascinating complexity to the system through the addition of more masses. We can continue to analyze these like we did for two masses, and we will again find that the movement is not periodic. There is a lot about this topic that I sadly did not have the time to mention, such as its relation to linear algebra, Fourier transforms, the superposition principle, and a lot more, so let me know if you'd be interested in me making a follow-up. Thank you for watching, and I hope you enjoyed!